Hey guys, we're going to take a look at the second worksheet, worksheet 2 here, and let's just get going. So we know the weight of our object here in the first problem is 25 newtons. Okay, so that is a weight. Mass times gravitational acceleration. We're also given a height, 2.10 meters, and we're asked to find the potential energy with respect to the ground. So our setup here looks like this, where potential energy is equal to mass times gravitational acceleration times height, which is then equal to weight times height, because mg is our weight, as you can see there. Okay, so we then plug in our numbers, and we get 52.5 joules. Okay. For the second one, we would need Hooke's law to solve this problem, and you guys have not studied Hooke's law, so we're going to skip number 2 here and move on to number 3. Okay, so for number 3 we have a box, 2.75 kilograms, and it's at the top of a frictionless incline. So you're asked to find the potential energy. So we have some information here that we don't actually need. The 10 meters would be the length of the incline, but we're given the height of the incline as 7 meters, and that is the value that we're going to need. So once again, we just do potential energy as given by mass times gravitational acceleration times height, and plug in our values as needed, and we get 189 joules with 3 significant figures. By the way, guys, if you notice any mistakes, please don't hesitate to let me know. All right, next one, number 4. You guys can still solve this one, but it would help if we defined equilibrium position. So I've drawn it on the diagram. The equilibrium position, in theory, is where the net force on this system would be 0. If we set that pendulum to swinging, then we actually don't have equilibrium there. We'll look at that more in IB physics, but the net force will not be equal to 0 due to centripetal force. We don't need to worry about it right now. Okay, so potential energy with respect to the equilibrium position will be given by this equation, where we have delta potential energy, and remember that a delta just means a change in potential energy, and that's what we're looking at here. So our change in potential energy is going to be equal to mass times gravitational acceleration times a change in height. So that is what we're interested in. So our change in height is just going to be given by the maximum height minus the minimum height, where the pendulum is in its equilibrium position. Okay, so we plug in all our values then into a calculator, and what we find is that we have 4.9 joules. Okay, for number 5, 2 kilogram crate is, 2 times 10 to the 3, 2,000 kilogram crate is pushed to the top of an incline, as shown here. Once again, what is the potential energy of the object when it is at the top of the incline with respect to the bottom? So here again, all we're interested in is the height. We're not really interested in the hypotenuse there, the length of the slope. So our height is given, our height gives us our potential energy, and here we go again. One last time, one very simple calculation. Okay, so now you're thinking, hey, this is super easy. So the question, how much energy was wasted as heat? Well, in order to figure that out, first we need to consider the work done on the box. So the work done on the box is given by force times distance, as you can see here. And our force is 12,000 newtons. Our distance is 12 meters. That will give us 144,000 joules or 144 kilojoules. Well, the energy wasted then is just going to be equal to the amount of work done minus potential energy. So we just subtract 118 kilojoules from the amount of work done, 144 kilojoules, and that will give us 26 kilojoules of sadly wasted energy. Happens all the time. Okay, guys, if you have any questions, please don't hesitate to let me know, and we will leave it there.